Okay, so in this problem, we want to draw the shear force and bending moment diagram for this beam. You can see it's a cantilever. So we're going to first start by finding our reactions and determining what the shear and moment will be at A. And then we'll use our differential relationships to complete the diagram. Also, if you look over here at the free end, there's information that will help us also with our shear moment diagram. You'll notice that this applied moment, what kind of bending moment is that? Positive or negative? Negative. So we would expect our bending moment diagram to hit that value, negative 100. And also this shear force is going to create what kind of shear? Reactive shear? A positive. So we'd expect a 60 kip positive shear at that end. So we kind of know where we're going to end, and we'll find our reactions, and we'll know where we begin. Okay? So let's go over here, and I'll go ahead and at A indicate my reaction. So I know my positive shear force at A is up, and my positive bending moment at A is in that direction. So we need to find those reactions. So the first thing we'll do is resolve this distributed force. The area under the curve will be the equivalent force, and it's a rectangle, so base times height. So we know that the concentrated equivalent force will be 4 per feet times 12 feet, or 48 kips. And more than likely we're going to sum moments about A, so we want the distance from A to the centroid, and the centroid of a rectangle is what? Halfway. So that'll be 6 feet. So that should give us enough. So let's solve for that. So I'm going to start by assuming right-hand rule for my sign convention, and I'm going to sum moments about A and make sure it's in equilibrium. Okay, starting at the left side, this moment that I've assumed here, this positive bending moment, with my sign convention and using statics, what kind of moment is that? It's a negative moment. The concentrated equivalent 48 kip force, what kind of moment is it creating about A? Positive or negative? Negative. Mr. Rippey, you've moved on me. I'm used to hearing you up in the front row.
Yeah, well, I was bumping my gum before class and switched back to it.
Oh, okay. I thought someone else was answering my questions for a change, but it was just you're in a different spot.
Mixing it up a little.
I like it. Mix it up. So what's the moment arm? From A will be 6 feet.
6 feet.
Then I get all the way out here. I've got this big 60 kip force acting at the end of the cantilever. What kind of moment is that? Positive or negative? Negative. So I got 60 kips, and what's its moment arm? Looks like 20 feet. And then I have the actual applied moment at the end, which, given this sign convention, or given this direction and this sign convention, it is negative. So with all that, I should be able to solve for the moment at A. It looks like it's going to be negative. I don't know what all that is. You guys are going to have to help me with that.
I have negative 1,488. Somebody help me check.
Anybody else get that? 1488?
I tried a new technique on my side.
Yeah, I got it.
Okay. So I got 1,488, and that would be kip feet. And it's negative, so it's negative moment. I'm sorry, negative bending moment. Okay, then I'm going to sum forces vertical, in this case the y direction, and make sure it's in equilibrium. And I'm going to assume up is positive. So again, starting on the left-hand side, I've got this shear force acting up. That's positive. 48 is down. That's negative. And 60 is down. That's also negative. So it looks like the shear at A is 108. So I have positive shear at A, negative moment at A, bending moment at A.
I think it's 15.
Yeah, 15.
What?
15.
Oh, I'm sorry. I just wrote it down wrong. I think you said that. I shorted you 100. Okay? So reactions, that's pretty easy. So now we can make a template. There's the extent of my beam, left and right. I'll go ahead and for the shear diagram establish a axis, positive x, positive shear. All my values will have units of kips. Also, I noticed that here at 12 feet, when this load becomes discontinuous, there might be something happening there, so I'm going to add that point to my template. So now we're ready to start. We'll begin here at the left side. We always like to move positive x, so we'll start here on the left. What is our our shear force at the beginning? Well, we saw for the shear at 108, and it's positive, so we're going to start off at positive 108. Now, we've already talked about here at the end, what do we expect the shear to be when we hit the end? Positive 60. So that's what I'm expecting. Hopefully my procedure will connect those 2 points. Now remember, the change in shear between any 2 points is the area under the load diagram. Right? It's one of our fundamental principles. So starting here, yes. Remember, if you look at this little spot, let me just kind of quickly draw you a free body diagram of that up in the corner. So I'll draw a little bitty chunk of the beam, a little tiny dx piece of the beam. And on the right side, I would have the force at 60 kips. And on the left side, positive shear will be up. So if you sum forces, you can see that, it's off the frame there a little bit, but you can see that it would be positive. Yeah, if when in doubt, you can just draw a little free body diagram there. Okay, so we're going to find the area under the loading curve, and that'll be my change in shear. So here's a good area to find from 0 to 12. What's the area of this loading curve?
48 kips.
48 kips. And is that a positive load or a negative load? Negative. So I've got 108 minus 48 gets me to 60. Now what's the shape of that curve? Well, I also know that the slope of the shear diagram is equal to the value of the load. So what is the value of our load everywhere in this first 12? We go up, it's always 4. In fact, it's always negative 4. So the slope is constant and negative. It looks like that. So again, if you were to look at that, you would see it would be 1 to minus 4 if it were to right scale. So I've got kind of a trapezoidal shear over the first 12 feet. Say it again. Question? I hear murmuring, but I don't hear a question. It's okay? It's all right? You're supposed to go, it's all right. That's too old. Okay, so what is the change, what is the load curve over the next 8 feet? It is 0. So there is no change. So 60 stays 60. That's good. And what is the shape? Well, the shape is given by the load. The load is 0, so I have 0 slope. Mr. Rippey, what is a curve with 0 slope? A horizontal line. See, all that tuition money is paid off for you. There you go. Still another quadratic equation. You don't have to know the quadratic equation. You just need to be able to recognize it. All right? That's what the FE says, right? They give you everything you need. You just have to be able to find it in that book and recognize it. All right, so let's put down the positive x, and that this will be our positive moment, and all of our values here will be in kip feet. So what do we know about our bending moment? What's it going to start with here at the left side? We found the bending moment. It was negative 1588. Are we sure that's right? Everybody check that again?
Yes, that's right.
Okay. So that means we're going to start at negative 1588. And what should we end at? 100. This is going to be not to scale, but you'll get the idea. So let's make sure that we can connect those 2 points. Now for the moment diagram, the change in moment between these 2 points is equal to the area of the shear. So you can see how these things build. The same principle we applied to shear using the load, we're now going to apply to moment using the shear. So if you get these ideas to be able to take the load to the shear, you're just going to repeat it with kind of the shear looks like the load now, and you're going to do it again for moment. So it says the change in moment is the area under the shear diagram. What's the area under this trapezoidal diagram? I don't remember that off the top of my head, but I do know to find the area of a trapezoid, you average the 2 endpoints, right? So that looks like that should be, what, 84? And it would be 84 divided by the base. So whatever 84 times 12 is, what's that? Excuse me. 1008. So that should leave me with 580. So I should land here. That should be 580. That's the change. Now, what is the shape of the curve? Well, the slope of the moment diagram is equal to the shear. Right? So let's examine the shear. So looking at the shear value, starting off, it's a very large positive value, and it decreases to a smaller positive value. So if I were to draw a slope, it might be a large value going down to a smaller value. So my curve would be quadratic and maybe look like that. So there's the distribution of moment. Now going back to our relationships, the change in moment is the area in the shear diagram. So now from 12 to 20, what's the area in the shear diagram? What's a rectangle? 60 times 8 is positive 480. So negative 580 plus 480 gives us negative 100. Works. And the slope of the shear the moment diagram is the shear. And what's the value of the shear? Well, it's constant in that region, and it's positive. So I have a constant positive slope, and it looks something like that. So this is trapezoidal, and then this is quadratic. So again, as a designer, what would you be interested in here? Where's the maximum shear? Well, as you might expect, it occurs at the cantilever. It's 108. And what's the maximum bending moment? As you would expect, it occurs at the cantilever, and it's fairly large, 1588, negative. So if I was making this beam out of concrete, where would I put my reinforcement, at the top or the bottom? How is this beam going to bend? It's all negative moment. Right, so it would bend like that. So you would have tension in the top and compression in the bottom. So yeah, you would have reinforcement in the top of the beam. Just kind of giving you a look ahead. So any more questions about that one? Mr. Max?
You said that formula was for figuring the area of the trapezoid?
You just take the average of the two ends. It turns it into an equivalent rectangle. So I took 108 plus 60 divided by 2 and then times the base. I do remember that. I don't remember where the centroid of a trapezoid is off the top of my head. There is an equivalent formula for that, but that one has not gone in and stayed, like a lot of stuff.
If you broke it into a triangle and a rectangle, would you still get the same answer?
For the area?
Yes.
Sure. Because the rectangle would give you 60 times 12, and 60 times 12 is 720.
Yes.
And then the height of the triangle would be 48 times 12 divided by 2. I think if you add those two together, hopefully you'll get the same thing. I'm really hoping you will. Did you get 1588? If not, we're in big trouble. I think it's correct because it all worked out. It matched up nicely. Okay.